Okay, so this week my question is, what are linear surface volume charge densities? And I'm going to explain when you use them. So before the linear charge density, we always used equations where there was a Q involved. Q being charge. Now, when we have a charged object and it's no longer a point particle, we have to use charge densities. So for number one, linear charge densities, we use the symbol lambda. And that's saying that if we have a line like this, it's going to have a charge. It's going to have a charge Q, but it's going to be per meter. So in a line, we have a coulomb of charge per meter. One of the equations we have for that is like an infinite line of charge. That equation looks like this. Electric field equals to K constant. There's our charge density for a linear object all over R. So now pretty much the same thing applies to something with a surface. So say we have like a surface, like a plane, like a plane, going off into all directions. We can no longer use lambda because this is no longer a one-dimensional object. So what we have to use is a charge per square meter, because we have two dimensions now. So just like area, we have areas in meters squared. This charge density is going to be in coulombs per meter squared, and that would find the charge per square meter. So all the stuff in here. Usually the variable for the surface charge density is going to be sigma. And the equation of a plane which has sigma in it is E, electric field, equals sigma over 2 epsilon. Next thing we have to define is now a volume charge density. So if you apply the same logic that we did for the two-dimensional thing and the one-dimensional charge and apply it to 3D, all we have to do is think of a 3D object, say a cube. Now we don't really have we haven't learned a symbol yet for the volume charge density, but we know it's going to be in units of coulombs per cube meter, because now we have a three-dimensional object. We have to think of the volume now instead of just the area.